this is lecture 35, and this is just an example of the continuous time Markov chain. So this is called the copier machine problem. Okay, so just to give you an overview of a problem, you have two copier machines that are maintained by a single repairman. So you can think about being at a school or something. You have two copier machines, and machine I functions for an exponentially distributed amount of time with mean 1 over gamma I. And so it has a rate of gamma I before it breaks down. The repair time for copier I are exponential with mean 1 over beta I. So what that means is that beta I is the rate at which the repairman can repair copier I. And we assume that the repairman can only work on one machine at a time. So basically, he works on the machines in the order in which they fail. So we're going to construct a continuous time Markov chain for the system with the goal of finding the long-run proportions of time that each copier is working and that the repairman is busy. Okay, so what should the state space be? Okay, so we need to think about what we're trying to do here. The order in which the copiers fail is important because he only works on one machine at a time, and he finishes working on that machine before he moves on to the next machine. So he's going to repair them in the order in which they fail. So we need to think about there being copier 1 and copier 2, and then the possibility that there are no copiers that aren't working. So our state space, if we think about it, we can have 0, in which no copiers are failed. So we can have 1 represent when copier 1 has failed, 2 to represent when copier 2 has failed. Now when both copiers have failed, the order is important because he's going to finish one before he goes on to work onto the other. So we're going to let 1, 2 be the state in which both copiers are failed, but one failed first. And 2, 1 be the state in which both copiers have failed, but 2 failed first. Okay, so the next question is, how do we draw a transition diagram using the rates of transfer? Well, first of all, we need our states. So here's all of our different states. We have no copiers failed, copier 1's failed, copier 2's failed, and then both copiers have failed, keeping track of which order they failed. So just to remind us of what the rates are, we have our rates, our fail rates, and our repair rates. Okay, so let's think about if we're here at no copiers have failed. So what can happen? Well, one thing that can happen is copier 1 can fail. So here, if copier 1 fails, then we're going to move to state 1. And what's the rate at which copier 1 fails? It's gamma 1. So the transition rate from 0 to 1 is this rate at which machine 1 is going to fail. Well, the other thing that could happen if you have no copiers failed is machine 2 can fail, and that's going to be at rate gamma 2. Because that's the rate at which machine 2 fails. Okay, so now here, if copier 1 has failed, what can happen if copier 1 has failed? Well, we could get lucky, and the repairman could fix copier 1. We could go back to no copiers failed. So here, the repairman fixes copier 1 at a rate of beta 1. We could get unlucky, and copier 2 could fail while still working on copier 1. So then we would have both copiers have failed. So here, if copier 1 has failed, and then copier 2 fails at a rate of gamma 2. So a rate gamma 2 is going to transition from 1 to 1, 2. Similarly, we can look at the same sort of thing for copier 2. So what is the rate, what's going to happen with copier 2? Well, we could go back to having none failed, and that's at the rate that the repairman can fix copier 2. Or if he's working on copier 2 and copier 1 then fails, then we could transition here to both copiers failed at a rate of the fail rate for machine 1. Okay, so now the other ones are if we're up here and machine 1 failed and machine 2 has failed. Machine 1 failed first, so basically if machine 1 failed first, then the first one that he's going to fix is machine 1, right? So if he fixes machine 1, then we're going to be left with just copier 2 has failed. So we're going to transition to 2 at the rate beta 1, where beta 1 is the repair rate for copier 1. And similarly, if copier 2 failed first, then we're going to fix it at a rate of beta 2, and so then we're just left with copier 1 failed. Okay, so now can we write down the transition rate matrix or the generator matrix for this continuous time Markov chain? Okay, so remember how to get the transition rates. To get the off diagonals, it's really just our rates at which we move from one state to the other. So here, if we're at 0, we're going to move to 1 at a rate of gamma 1. We're going to move to 2 at a rate of gamma 2. If we're at 1, we're going to move to 0 at a rate of beta 1, and to 1, 2 at a rate of gamma 2. If we're at 2, we'll move to 0 at a rate of beta 2, and to 1 at a rate of gamma 1. Then here, if we're at 1, 2, we can only move to state 2 at a rate of beta 1, and here to 1, we can only move to state 1 at a rate of beta 2. So these are our off-diagonal elements. So here, if we look, 0 can go to 1 at gamma 1, or to 2 gamma 2. So what goes on the off-diagonal is the negative sum of those, because remember, this has to add up to be 0. The column has to add up to be 0. Here, where can 1 go? Well, 1 can go back to 0 at that rate beta 1. 1 can also go to 1, 2 here at a rate of gamma 2. And then this diagonal element is just going to be the sum of those, negative sum of those rates. So we're going to have negative gamma 1 plus gamma 2 plus beta 1, and et cetera, et cetera. These are exactly the same things that I said. Here with 1, 2, and 2, 1, notice there's only one transition, so our diagonal elements is just negative beta 1 and negative beta 2 respectively. Okay, so now some specific questions. We want to actually figure out what the long-term proportion of time is that copier 1 is working, copier 2 is working, or that the repairman is busy. So we're going to give specific rates here. So we're going to assume that the rate at which copier 1 fails is once per month. Copier 2 fails 3 times per month. The repairman can fix copier 1 twice per month, and can fix copier 2 4 times per month. Okay, so if we stick those into the matrix that the Q form that we had before, then this is actually our generator matrix with their specific values. And this is what we're going to use to actually figure out when copier 1 is working, copier 2 is working, and the repairman is busy. So remember how we do this. We're looking for steady state, right? Because we want long-term proportions, so we want to know when Q pi is equal to 0. Q pi equals 0 means that we have steady state. The other thing that we have is the sum of our states have to be equal to 1. So here, let's write down our Q, and we can actually form an additional, so we want to know when our Q is equal to 0. So here we have our Q. We put zeros on this right-hand side. We also have that the sum of the states, so our state 0 plus state 1 plus state 2 plus 1, 2 plus 2, 1, the sum of all these states has to be equal to 1. So we can form this matrix. And we want to solve to see what our pi 0, pi 1, pi 2, etc. are. So we can do the reduced row echelon form of this. So here, when we do the reduced row echelon form, we get these values. These values here are our pi. So we want to use those to answer the questions. So what is the long-term proportion of time copier 1 is working? So copier 1 is working whenever we have no machines that are not working, or when only copier 2 is not working. All the other times copier 1 is broke, right? So the only time that copier 1 is working is if no machines are needing repair, or only copier 2 needs repair. So here this is none. This one is our copier 2, so we have 0.62. The long-term proportion of time copier 2 is working is 0.62. Similarly, we can think about copier 2, so this is going to be pi 0 plus pi 1. So here we pick off pi 0 and pi 1, so now copier 2 is working 0.46. The long-term proportion of time copier 2 is working is about 46% of the time. The long-term proportion of time that the repairman is busy, well, the repairman is busy pretty much all the time except for when no machines are working. So you could really just do 1 minus pi 0, which is 0.66. So the repairman is busy a lot of the time, or the majority of the time. So one of your homework problems is an alternate repair strategy. So in this one, you're still assuming that so you're going to have different state space. So here you're assuming that copier 1 is now more important than copier 2. So it's most important to have copier 1 working. So if copier 1 is down at any point in time, then you always will fix copier 1 first. So it immediately shifts attention to copier 1. So you're going to really complete the same questions as before, keeping in mind that if copier 1 is broke, the order does not matter anymore. You have to fix copier 1 first. Okay, so next time we're going to actually talk about birth and death processes, and this is a lot of stuff that's done in continuous time markup chain, is using birth and death processes.